Record. Okay. So you go to the share screen and look at let me show you where it is. We are in week 6, right? So week 6 is this one. So this is the tutorial sheet for today, and there are, I think there are 10 questions. There are 10 questions. I will try to do as many of them as possible. I may not be able to do all 10 of them, but I will see. I'll try my best. Right? Okay. Now, as usual, if you have, I mean, whatever question you guys have, please feel free to use the chat room. Right? So, please use the chat room as usual. Right? So, let me start with one of the questions. So, let me change the camera. Can you see this, guys? Maybe not so clearly, but I will try to refocus if possible. All right, so I will start with question number 10 first, because I think that's most relevant to what we've been doing. All right, so question number 10, I don't know if you can read it or not, but you should be able to see, I mean, if you have a laptop, you should be able to see question number 10 on your laptop. It says that you have IID, NIID random variables, which are binomial with parameters m and p, where p is unknown, and we are considering this estimator for p, and the question is to find the bias and the variance of p hat, and say what happens as n goes to infinity, right? All right, so let me start with question 10. This is question 10 I'm starting with, right? If you can't see it, guys, please let me know. So basically, you have, the question says the following: you have n data points, right, which are IID with binomial distribution with these parameters m and p. And the question is that you are given this estimator p hat, which is x bar plus 1 divided by n plus 2. Right, the question is to find the bias and the variance of p hat. All right, so let's start with the bias first. All right, the bias, remember, the definition of bias is the expected value minus the parameter that you're trying to estimate, right? Which is the, guys, as usual, if you have whatever question you may have, please feel free to use the chat room. I will try my level best to answer them. Okay. Okay. Now, taking the expectation inside, you can write this as follows. You get this plus, yeah, right? Now, x bar, remember x bar is the average, so you can write this as the expectation of x bar, which is 1 over n, right? Okay, guys. Now, you should take the expectation inside this summation. You will get this, right? Now remember, for a binomial variable with parameters m and p, I'm sure you guys know from probability 1 that the expectation of a binomial variable is n times p. So what you have is this, right? MP is a constant with respect to I, so what you have is this. Now this simplifies to m p plus 1 divided by n plus 2 minus p. So this is the bias. Okay, this is the bias of the estimator. Now as, are you guys okay with me? Yeah. As n goes to infinity, what this goes to 0, this goes to minus p as n goes to infinity, right? So what you can see is p hat is not biased, and is also not asymptotically unbiased. Remember, asymptotically unbiased means that an estimator which goes to the bias of which goes to 0 as n approaches infinity is said to be asymptotically unbiased. But in this case, the bias, which is given by this, approaches minus p as n approaches infinity. So therefore, p hat is not asymptotically unbiased. Okay. All right, guys, are you okay with this? Are you for? I mean, any questions? Please use the chat room, guys. All right. So that's the first part of the question. The second part of the question is to find the variance. Of p hat, right? All right. So let me start. So to find the variance of p hat, right? This is going to be the variance of x bar plus 1 divided by n plus 2, right? Now you may recall that, all right, let me write it down in a few steps. You may recall that the variance of a random variable plus a constant is the same as the variance of the random variable. This is something you should have learned in your probability 1. Do you remember this? That this is equal to this, because this is a constant, so it doesn't change the variance, right? Now n plus 2 is also a constant, so you can pull it outside. So this becomes n plus 2 squared times the variance of x bar, right? Now variance of x bar, you guys know, is the sample variance, sorry, the sample mean. So you can write it like this. Yeah, you follow me? Right. Now, taking the variance inside, n is a constant. When you pull it outside, it becomes n squared. So this is n plus 2 squared multiplied by n squared times the sum of the variance of xi. Now remember, xi is a binomial variable, right, with parameters m and p. I'm sure you know from probability 1 that the variance of a binomial is NP times 1 minus P. All right. Okay. Now this is a constant with respect to I, right? So this will be yeah. All right. So this becomes it. Remember, sum of a constant is n times the constant, right? So this becomes equal to, if you simplify, this is equal to n plus 2 squared divided by n, and this approaches 0 as n approaches infinity. All right, so this completes question number 10. So what I would, if you're just joining me, the question that I just done is question 10 on the tutorial sheet number 6, right, which is this one. So I just completed question 10. Are you guys okay with this? Or you have questions? I mean, please let me know. Are you okay with? Yeah, all right, thank you. All right, so let's go back to the tutorial sheet where, so I've done question 10, we are done with this. Right, now question 9, you have a random sample from a uniform distribution 0 theta, where theta is unknown. The first part is to find the constant k such that theta hat k times x bar is unbiased for theta. Right, so that shouldn't be too difficult for you guys to do. All right, so I'm gonna do now, I'm doing the tutorial sheet in the reverse order, starting with the last question and going backwards. So this is question 9. So you have a random sample x1 to xn, which are IID from a uniform distribution on the interval 0 to theta. And you have this estimated theta hat equal to k times x bar, where x bar is the sample mean. The first part is to find the k such that this is unbiased for theta. So what we need to do is to find the bias of theta hat and set it equal to 0. Now remember, the bias is, this is the definition of bias, right? So this is expectation of k times x bar minus theta. Now k is a constant, so you can pull it outside. Yeah. X bar, you can write it like this. Take the expectation inside the sum, you get k divided by n times the sum of the expectation of xi minus theta. Now, you know from probability 1, the expectation of a uniform variable. Do you guys remember or not? Do you guys remember? Okay, if you don't remember, let me write it down. If x is a uniform variable on the interval a to b, then the expectation of x is a plus b divided by 2. This is something I'm sure you guys learned this in probability 1. Maybe, I don't know, if you didn't, if you don't remember, this is the formula. This is the formula, right? Now, if you use this formula to this, you get theta divided by 2, right? Minus theta, right? Okay, guys, so this is k over n. The theta by 2 is a constant, so it's n times theta by 2 minus theta. All right, so this becomes k theta by 2 minus theta, right? And this is equal to 0 if k equal to 2, right? Okay, so what you can say is that theta hat equal to 2 times x bar is an unbiased. Remember, an unbiased estimator is an estimator which has bias equal to 0. Are you okay with this, guys, or not? This is the first part of question 9. Are you okay? Are you sure? I mean, if you're not okay, please feel free to say so. I'll try to go over again. Okay, the second part of question 9 is to find the variance of theta hat, right? So that's what I'm going to do now. So I'm going to find the variance of 2 times x bar, right? So this is, I'm going to find the variance of 2 times and see what happens as n goes to infinity. Okay, so this is, if you take the 2 outside, it becomes 4. So it's 4 times the variance of x bar. And this is 4 times the variance of okay. Now if you take the n outside the variance, it becomes n squared, right? Times the sum of the variance of xi. Now you should know from probability 1, guys, like let me write it down if you don't remember. If you have a variable x that has the uniform distribution on the interval a to b, then the variance of that variable is equal to this. Do you remember this, guys, or no? This is the formula for the variance of a uniform variable, right? Okay. Now, if you use this formula, you get 4 divided by n squared times the sum from 1 to n of this guy here becomes theta squared divided by 12, right? So this is 4n squared multiplied by n theta squared divided by 12, because this is a constant. So this simplifies to theta squared divided by 3, and this approaches 0 as n approaches infinity. All right. Okay, guys. So this completes question 9. You okay with this or no? You sure? All of you? All of you are okay? Okay. Yeah. All right. So that's question 9 done. Now the next question I want to do is question 8. So we're done with this. Question 8 is, okay, you have, if you can't read this, just I suggest you read it on the laptop that you have, right? Okay, so please, so it says you have a random sample from a population with mean equal to 0 and variance sigma squared. And the question is to find the constant k such that this estimator is unbiased for sigma squared. So again, it has 2 parts. Question 8. All right. So you have this. Excuse me. You have this estimator you have this estimator, right, for sigma squared. And we want to find the K, right? We want to find the constant K such that this is unbiased for sigma squared. So what we need to do is we need to find the bias, which is the expectation of, remember the definition of bias is always the expectation minus the parameter that you're trying to estimate, right? So this is going to be the expectation of K times all right. Okay, K is a constant, so you can pull it outside. So this becomes K times the expectation of okay. All right, the next thing I'm going to do is I'm going to take the expectation inside the sum. All right, so this becomes K times the sum okay. All right, the next thing I'm going to do, I'm going to use the following trick. I'm going to use you see in a minute why I'm doing this. You see what I have done here. I have subtracted this term and added the same term, so I haven't changed anything. All right, now, okay, let me ask you something. Let me ask you something. What do you know about what do you know about this? This is what you have here is the expectation, is the variance, right? So what you have is the following. You have the variance of xi plus the square of the expectation of xi minus sigma squared. All right, now you should go back to the question. The question says that the population has mean equal to 0, right? And the variance equal to sigma squared. So this guy here is equal to sigma squared, and this guy here is the mean is equal to 0, right? So what you have is K sigma squared plus 0, right, minus sigma squared. Okay, right, now sigma squared is a constant with respect to I, so what you have is K times n times sigma squared minus sigma squared, and this is equal to 0 if K is equal to 1 over n. Right, so that completes the first part of question 8. Is it clear? So you see the trick I applied here. The trick is to use this, subtract this term and add the same term, so that you can use the fact that this guy here is the variance of xi. All right, guys, are you okay with this or no? Okay, thank you. All right, so that's the first part of question 8. The second part is to, if xi are independent normal with 0 mean and variance sigma squared, what is the sampling distribution of the estimator? All right, so let me show you how to do part 2. So we just determined that K is equal to 1 over n. All right, so you just determined that k is 1 over n. So the estimator that we have, is the following, is 1 over n times the sum from 1 to n of xi squared, right? Now, in part 2, we are told that xi squared is normal with parameters 0 and sigma squared. Okay. Right now, what I'm going to do is the following. I'm going to divide this by sigma, right, and multiply by sigma. You will see why I'm doing this in a minute. Now, if you divide a normal variable by sigma, what do you get? I mean, and okay, let me take the sigma outside. So it becomes sigma squared by n times this. Okay. Now, a normal variable divided by sigma is the standard normal variable. Remember, when you standardize a normal variable, you divide by the standard deviation, right, which is sigma here, right? So you get the standard normal. Now, if you look back, if you look in the I don't know, you might have forgotten now, but if you look at the video on chi-squared, which we covered some time ago, one of the properties I mentioned is that if you square a standard normal, what you get is a chi-squared with 1 degree of freedom, right? So please look at if you already forgot it, please look at the video on chi-squared distribution, right? All right, and another property that I mentioned in the same video is that if you sum two different chi-squared, then what you get is also a chi-squared with the degree of freedom being the sum of the degrees of freedom, right? So in this case, you have n different chi-squared, and you're summing them. So what you're going to get is a chi-squared variable with the degree of freedom being the sum of 1, is the sum of 1 for I from 1 to n, which is n. All right, so please, if you want to know where this come from, if you want to know where these two steps came from, please look at why is it squared? Because you have a squared here, hang, right? This guy here reduces to n01, right? So what you have is the square of n01 because of this. You have, I mean, from the beginning, you have a squared here, and a squared here, and a squared here, right? So you need to keep the two all the way, right? So what you get here is a square of the standard normal variable, standard normal variable, which if you look at the video, you will see this is a chi-squared with 1 degree of freedom. And again, the sum of a chi-squared is chi-squared n. All right, guys, so this completes, is this okay or not? This completes question 8. Hello, guys, talk to me, please. This is, everybody okay? Not everybody is talking to me, guys. Are you sure? Okay, thank you. All right, so that completes question 8. The next question I'm gonna do is question 7. So that we are done with this. Question 7 is this: you have a random sample from a normal with mean equal to 48 and variance 36. The first part of the question is, what is the probability that, excuse me, what is the probability that the sample variance is between 25 and 60, right? Okay. All right, so let me see how we can do this. So this is question 7, guys. So you have a random sample x1 to xn. X10. You have a sample size of size 10, which is IID, with parameters mean equal to 48 and variance equal to 36. Okay. All right. The part one is to find the probability that the sample variance. Remember, the sample variance is between 25 and. This is the notation that we use for the sample variance. You may recall. What do you mean, Hank? The size of IID be different? Yes, they can be different. I mean, in this case, the size is 10. So you have a sample of size 10 from a normal distribution. Yeah, so you have a sample of size 10. So this, if you look at the formula that I gave you for sample variance, there are two formulas I gave you. One is the biased version, the other one is the unbiased version. So in this case, I'm going to use the unbiased version, which is 1 divided by n minus 1, which is 10 minus 1, times the sum of okay. All right. Do you see where this comes from, guys, or not? This is the formula I gave you at the beginning of the course for the sample variance. All right, so 10 minus 1 is 9. Now, if you multiply by 9 across, you get the probability that 9 times 25 less than or equal to okay. All right, the next thing I'm going to do is I'm going to divide everything. Do you understand, Hank? I mean, did I answer you correctly? I mean, did you understand what I said, Hank? Because here we have a sample of size 10, so the sample size is 10. But you can have another, I mean, you can have a sample size of 20 or 30 or 100 or 1,000. So it doesn't matter what the sample size is. I don't understand your question. I mean, I will get back to you later, okay? All right, now what I'm gonna do is, all right, I'm gonna divide everything here, this one, and this one by the sample variance, which is 36, right? So I'm gonna divide by, you will see in a minute why I'm doing this. The reason I'm doing this is because of a property that we talked about in the class. All right. Do you remember the property that, which is this, right? Let me write down the property in case you forgot. You should have a random sample, which are IID, right, with parameters, say mu and sigma squared, right? Right. Then the following is true. Do you remember this property, guys, or not? I mean, this is a property I talked about in the video on chi-square distribution. Okay, some time ago, right? So that's why I divided by 36, because 36 is the variance, right? Okay, so using this property, right, this line here can be written as this simplifies to 25 by 4, right? Less than or equal to chi squared with n minus 1. N is 10, so this is going to be 9. And this guy here simplifies to 15. All right. Are you with me, okay, guys? Hello, talk to me. If you're not okay, please use the chat room, guys. Okay. Now this guy you can write as okay. Like this, right? That's the difference of these two, right? And this you can write as, this is what you have here is the CDF of a chi-squared variable with 9 degrees of freedom at 15. And what you have here is the CDF of a chi-squared variable with 9 degrees of freedom at 25 by 4. Right? Okay. Now, if you have if you're using R, you can compute this. In R, you can compute this. This is the notation I use for the CDF, right? You can compute this as P chi-squared. Remember, P chi-squared is the notation to compute the CDF at 15 with the degree of freedom df equal to 9. Okay, and this guy here can be computed as P chi-squared at 25 by 4 with the degree of freedom equal to 9. All right, so this completes the first part of question 7. Are you okay with this, guys, or not? Before I go to part 2, please talk to me, guys. Are you tired or what? Hello, guys. Everybody okay with this? Okay, thank you, guys. So let me do part 2. Part 2 of question 7 is to find the sample size such that the probability that S squared is greater than 20 is 0.9. All right, now let me show you how to do this. I know I may run out of time, but let me show you. This is part 2, question 7, part 2. So we want to find the sample size so that the probability that s squared is greater than 20 is 0.9. Now remember, s squared is the sample variance, so it's 1 over n minus 1 times the sum yeah. All right, now if you multiply across by n minus 1, you get this. You see why I'm doing this, guys. The reason I'm doing this is because I want to use the result that I used in part 1. All right, to use that result, I need to divide by sigma squared, which is 36. So I'm going to divide both sides by 36. Right. Okay, now using this result that I mentioned, a minute ago, right? We can say that the left-hand side here, has a chi-square distribution with n minus 1 degree of freedom, right? And the right-hand side can be simplified to this. Yeah. Now this you can write as 1 minus the probability that less than or equal to 5 times n minus 1 divided by 9 equal to 0.9. Yeah. All right, so if 1 minus this is equal to 0.9, then the probability that chi-squared n minus 1 is less than or equal to 5 times n minus 1 divided by 9 should be equal to 0.1. You follow me, guys, so far or not? Right, now what you have here is the CDF, the cumulative distribution function of a chi-squared variable with at 5 times n minus 1 divided by 9 equal to 0.1. Right, now if you're using R, you can compute the left-hand side as P CHISQ, in other words, the probabilities of chi-squared at 5 n minus 1 divided by 9 with the degree of freedom df equal to n minus 1, and this is equal to 0.1. Right, now if you, sorry, this is 9, guys, if you can't see it, sorry for my writing, this is 9. Okay, now if you solve this in R, right, you will get n. I mean, there are functions for solving this in R. If you do that, you will get the sample size to be approximately equal to 15. All right, guys. Are you okay with this? Or this is part two of question 7. Guys, talk to me. Are you okay? All right. So that completes question 7. The next question is so we're done with question 7. The next question is this one. So it has two parts. The first part is that you have a random sample from a Poisson distribution with parameter lambda. Lambda is unknown. And what are the mean and the variance of lambda hat equal to x bar? All right, let's see how we can do that. I only got 5 minutes left, but all right, I will see. I will try to do what I can. Okay, so this is question 6, part 1. So you have a random sample from a Poisson distribution, and you have lambda hat is given by x bar. Lambda hat is an estimator for lambda, right, taken to be the sample mean. All right, what we want to find is the mean and the variance of the sampling distribution of x bar, right? So to find, okay, let's try to find the mean first. Right, so this is the expectation of x bar, right? Yeah, and this is gonna be the expectation of this. Taking the expectation inside, you get I'm sure you know from probability 1. Now, what's the expectation of a Poisson variable? I'm sure you guys know. Is equal to, hello guys, talk to me. The expectation of a Poisson is lambda, right? Okay. Yeah, so this is going to be 1 over n times lambda, which is equal to lambda. So that's the expected value of lambda hat. And similarly, you can find the variance. To find the variance of lambda hat, you say variance of x bar, right? Which is the variance of 1 over n times the sum of xi. Right, if you take the n outside, it becomes n squared times the sum of the variance of xi. Now, I'm sure you know from probability 1 that the variance of a Poisson is also lambda. So this is 1 over n squared times the sum of lambda, right? So it's 1 over n squared times n lambda, right? And this is lambda by n. All right, are you okay with this or not? Hello, guys. So the expected value is lambda and the variance is lambda by n. Yes? You guys okay with this? Yeah. All right, so to answer, that's the question, that's the answer for part 1 of question 6. Part 2, I don't think I have the time to do part 2, but part 2 is just to use a normal approximation to the Poisson probability. So basically, you're looking for the probability that the sample mean is between 35 and 37, right? When lambda is equal to 36. So by the way, so since this is, we can say here in part 1, you can assume that lambda hat is approximately, it's an approximation, right? Approximately normal with parameters equal to lambda, the mean parameter equal to lambda, and the variance parameter equal to lambda by n. All right, so that's part 1. But to do part 2, if I have time, I may only have 1 minute. Oh, I've already run out of time. if you don't mind, I know if you don't mind, can I do part 2 now? I know I have run out of time, guys, but would you mind doing part? If you don't mind taking your time for a second. The question here is to find the probability that X bar is between 35 and 37. Okay. All right. So now we are assuming that X bar from the previous part, we are assuming that X bar is a normal variable with these parameters, right? This is an approximation. You should say approximation, right? Now lambda, we are told lambda is 36, right? And we are told that n is 100, right? So this is what you have, right? Now what I'm going to do now is I'm going to standardize. Remember how to standardize? You subtract the mean and you divide by the standard deviation. And you do that over here too. You subtract the mean and divide by the standard deviation. Okay. And what you have in the middle is the standard normal variable, right? Okay. Now you can write this as the difference of these probabilities. 37 minus 36 is 1 divided by the square root of this, right? Minus the probability that n01 is less than 35 minus 36 is minus 1 divided by the square root of this, right? Okay, now this guy, you can read it off the table. This is simply phi at 100 divided by 36, the square root. And what you have here is capital phi minus 100 divided by 36 square root. All right. Now, if you read this off the table, this is what you will get: 0.90 9044. So that completes part 2 of question 6. Sorry for taking your time, guys, but I hope you followed what I did. I'm sorry I haven't been able to do all the questions in the sheet, but on Thursday this week, I will post the full solutions to all 10 questions in the tutorial sheet. So it will include, sorry, question 8. Somebody is asking question 8. This is question 8, sir. This is question 8, which you want to see again. Sorry, on Thursday of this week, I will post the full solutions to this tutorial sheet, including typed solutions, handwritten solutions, and video solutions. So there will be three different versions of the solutions: typed solutions, handwritten solutions, and video solutions. All right, so I'll see you guys later. Take care of yourself and have a great day. Have a great afternoon or evening or morning, wherever you are. All right. And as usual, any questions you guys have, please feel free to contact me by email, Skype, Zoom, or phone. My phone number I've already given to you is 0161-273-2941. All right. Have a good day, guys.